In today's AI Explained, we are going to be talking about productionizing generative AI at scale. This week has been a very exciting week, as you probably have seen the launch of Llama 3.1, an open source model from Meta, which seems to really come very close in terms of accuracy to the closed source models. It's an exciting time that we are living in, and I'm actually the founder CEO of Fiddler AI. For those who don't know, I'll be your host today. Please put in your questions in Q&A box at any time during this fireside chat, and we'll also be recording this session. So if you want to see it later or share it with your friends and coworkers, please feel free to do so. We have a very special guest today. That is Robert Nishihara, CEO of Anyscale. Robert, you can turn on your camera now. So welcome, Robert. So just a brief intro about Robert. Robert is one of the creators of Ray, a distributed framework for scaling Python applications and machine learning applications. Ray is used by companies across the board, from Uber to OpenAI to Shopify to Amazon, to scale their ML training, inference, data ingest, and reinforcement learning workloads. Robert is one of the co-founders and CEO of Anyscale, which is the company behind Ray. And before that, he did his PhD in machine learning and distributed systems in computer science at UC Berkeley. And before that, he majored in math at Harvard. So excited to welcome you, Robert. Thank you for sharing this opportunity with us.
I'm excited as well. Thanks for having me on.
Awesome, Robert. First up, I would love to listen to you. How did you get into Ray? Like how give us a brief intro into Ray and the Anyscale founding story.
Yeah. So today I'm spending all of my time working on distributed systems and systems for AI. But in grad school, I started grad school with no background in systems. And actually I was spending all of my time more on the theoretical side of AI, trying to design algorithms for deep learning training or reinforcement learning, and proving theorems about how quickly these algorithms could learn from data and converge. And so it's really coming from that side of things. But what we found, and me and my other coworkers in grad school, was that even though we were trying to spend our time designing algorithms, we were actually spending all of our time managing clusters and building systems and writing code to scale compute or manage GPUs and things like that. And that wasn't, there wasn't an off-the-shelf tool that we felt we could just use to solve these problems. We ended up, and it wasn't just us doing this, right? A lot of other researchers in AI were building their own tools and building their own systems for managing compute. And we felt that the tooling here was really a bottleneck for AI research. And so we thought there was an opportunity to try to make that easier. And we started Ray, which is an open source project. Our goal was just to build useful open source tools to make it easier for people doing machine learning to take advantage of multiple machines, to scale in the cloud, to sort of solve the distributed systems challenges for you around dividing up the work across different machines, scheduling different tasks on different machines, recovering if one machine crashes, moving data efficiently. There are many different software engineering challenges around scaling compute, and we just got started building Ray to really try to solve these challenges. And one of the things that the underlying thing here is that AI was becoming more and more computationally intensive. And that was kind of the core premise of all of this, that people needed to scale things in the first place. If you could do all of it on just your laptop, there wouldn't have been any problem to solve.
Yeah, I remember those days when I was an ML engineer at Bing Search in 2000s. We would train simple models on our desktops, and the world has changed a lot now. And you guys are working with some amazing tech-forward companies like, OpenAI, Uber, Pinterest, talking about it before the call. What are some of the challenges that Ray helps solve for these type of companies that are, when they are building these large scale AI models?
The challenges have changed over time. I think for a lot of companies, have gone through, or even now are starting to go through a transition of adopting deep learning. Okay, so this is something that you mentioned Uber. They were a pioneer in machine learning and machine learning infrastructure, and had been doing machine learning for many, many years. And of course, the starting point for them was not deep learning. It was smaller, simpler models like XGBoost before. And when they went through this transition of really enabling deep learning in all of their products, the underlying infrastructure challenge and systems challenge got a lot harder because far more compute intensive. All of a sudden, you need to manage GPU compute instead of just CPU compute. You need to manage a mixture of them.
Mm.
And that is, you end up with potentially a different tech stack for deep learning and a different tech stack for classical machine learning. And it's sort of like providing all of these capabilities internally to the rest of the team is can be quite challenging. I mean, we see all sorts of challenges around. One is just enabling distributed computing, right? Enabling distributed training, things like that. But there are other challenges around, going the handoff from training the model, developing the model, to deploying it, right? We hear people say it takes us, 6 weeks or 12 weeks to get from developing a model to getting it into production. And that could involve, handoff to a different team, rewriting it with a different tech stack. And there's a lot of challenges that people face are around just how quickly their machine learning people or data scientists can iterate and move, right? Are they spending most of their time focused on the machine learning problems, or are they spending most of their time managing clusters and infrastructure?
Yeah. So let's go a couple of levels deeper, right? So I think distributed training is a very interesting problem. Let's basically, maybe you can walk us through what would it take, are you like, how does the architecture look like? Are you sort of like sharding the data towards these different replicas? How do you maintain the state? Give us like a taste of under the hood, or what makes Ray such a robust platform for distributed training.
And that's a great question. And just before I dive into training, there are three main workloads that we see people using Ray for. It's quite flexible, but training is one of them. Serving and just inference is another. And then the last is data processing, like data preparation or ingest and pre-processing. And companies typically have all of these workloads, and they're all challenging. We see a number of challenges around training. The first is just going from a single machine to multiple machines. But a perhaps more subtle challenge is, as you're scaling training on more and more GPUs, and you mentioned Pinterest, this is a challenge that it was one of the reasons Pinterest adopted Ray for training their models. As you're scaling training on more and more GPUs, it's very easy to become bottlenecked by the data ingest and pre-processing step. So you may want, a lot of training. Training is expensive because the GPUs are expensive. So you want to keep them fully utilized. And that means feeding the data in, pre-processing the data, loading the data, and feeding it in fast enough to keep the GPUs busy. And that may mean you need to scale the data ingest and pre-processing even more, right? And so that can often be done on cheaper CPU machines. So you want to scale up the data ingest and pre-processing on a ton of CPU machines, a separate pool of CPU compute, and then pipeline that into training on GPUs. It's conceptually simple, but hard to do in practice. And both of these things you may want to scale them elastically. You may need to recover from failures if you're using spot instances or things like that. There are other challenges you run into at even larger scales around actual GPU hardware failures and recovering quickly from that. In the regime where you start to have really large models, model checkpointing and recovering from checkpoints can be quite expensive. And so you need to build out really efficient handling of checkpoints. So there are many challenges. Those are some of the challenges that Ray solves. And just to call out the data ingest and pre-processing pipelining in, that is an area where we're seeing more and more AI workloads becoming not just requiring mixed CPU and GPU compute, and really being both GPU intensive and data intensive. And that's a regime where Ray does really well.
Got it. So these days, I mean, of course, like larger technology companies like Uber, Pinterest will be probably building and training models from scratch. But a lot of the enterprises that we work with at Fiddler, they are looking forward to and are already working with these, pre-trained models. There is the Llama 3.1 launched this week, and basically there's quite a few other options. There's closed source models like GPT and Claude. So where does Ray fit into this equation? So if I'm like an enterprise customer, I'm looking to build this conversational experience, with like using one of the pre-trained models, how can I leverage Ray to fine tune or, kind of build this model, build this LLM application?
That's a good question. So not every company is going to be training really large models, right? Although I do think the vast majority of companies will train some models. But what every company will do for sure is they'll have a lot of data and they'll use AI to process that data and extract insights or draw conclusions from that data, right? And it may sound like just a data processing task, but there's going to be a lot of AI and a lot of inference being used in doing that, because you're going to want to draw like intelligent conclusions from your data. And that is, again, a workload that will combine, it won't just be inference. There will be sort of regular processing and application logic combined with AI. And so this is something that also falls into the regime of, I think, like large scale processing, mixed CPU and GPU compute, combining machine learning models with other application logic. And this is, of course, when you think of large scale data processing, you might think of systems like Spark, which are mature, battle tested, and fantastic for data processing, but are also really built for a CPU centric world, right? And not really built with deep learning in mind. And so when it comes to scaling data processing in a way that uses deep learning, in a way that uses GPUs, and is often working with unstructured data like images and text and video, then you end up with a hard data processing problem where you have you're scaling on CPU compute, GPU compute, you're running a bunch of models, and these are the kinds of challenges we're seeing today that that we can help with.
Yeah. So it seems to me that Ray is definitely could be a platform of choice if you're thinking about scaling your model training inferences, especially optimizing your GPUs to the fullest extent possible. And it seems like that is like the unique sort of advantage. Now, when it comes to productionization, right? So, like basically you mentioned something about LLM inferencing and ML inferencing. And how does that work with Ray? And, what are some of the aspects of that you're trying to solve there? What are some of the challenges that you've seen, in productionizing, Gen AI and also your traditional machine learning workloads?
Yeah. And so with inference, we tend to divide it into online inference, where you're powering some real-time application, right? And offline inference, where you're perhaps processing a larger data set and you care less, it's less latency sensitive and more throughput or cost sensitive.
Okay.
So with, the challenges we see around online inference, these are things like, the challenges actually change over time as you're building AI applications, right? We see we were talking about this the other day, but as businesses start adopting AI, they're often in this exploratory phase where they're trying to figure out how to use AI in their business, what product even makes sense. And so at this point, the question is about quality. Are the models good enough? Right? Is the quality high enough? How do I fine tune to improve the quality? How do I reduce hallucinations, use RAG, all these kinds of things? And they care about iteration speed just for experimentation. And there's also a lot of data pre-processing that has to be done at this stage to see if you can just get your data into the model in various ways. Then once they figure it out, once they validate, hey, this is the right product, it makes sense, people like it, and you start moving these applications to production, then the challenges change, right? At this point, you might start to care about cost, right? You might start to care about latency. Is it responsive enough to, for people to really engage with it? Reliability, like how do I upgrade the models? Right? So the nature of the challenges changes. It always starts with quality because that's just what determines if it's possible or not. But once you meet the quality bar, then the criteria very quickly changes to latency and cost and other factors.
Got it. And so that's actually a very good point you mentioned, reliability. Like, one of the things that when you're productionizing model inference is like, how do you upgrade the models? How do you swap an existing model with a challenger model that you actually have trained? How do you deal with that? How does RAID help developers do these things where you upgrade those models, you iterate on A/B test model versions, or like move from champion to challenger, and in a manner that you're not affecting anything from latency or throughput and all those things?
Yeah, great question. So the challenges are different for large models and for small models. For example, we see companies that want to deploy thousands of models, right? That might fine tune or train one model per customer of theirs. And if they have thousands of customers, they end up with thousands of models. And they might be low utilization models. And so they end up needing to, there's the operational challenge of managing and deploying many, many models. There's an efficiency question of how to, perhaps serve all of these models from a shared or smaller pool of resources. With larger models, the challenges end up being around GPU availability and things like this. And just to give one example, as you deploy a model and then you upgrade a model, a natural way to do that is to sort of deploy you have the old model that's serving in production, then you deploy the new one, and then you slowly shift traffic over.
Yeah.
And that done naively will require double the amount of GPUs, right? And so can you do this without requiring that many extra GPUs? Can you do it kind of in place or with maybe one extra GPU? And so there are all sorts of challenges around making that work well.
Right.
There are things like you may have bursty traffic, right? If you have to reserve a fixed pool of GPUs, but then you have bursty traffic, there's going to be a lot of times when you're sort of provisioning for peak capacity, but you have unused capacity. And can you, run other workloads? Can you multiplex other less critical workloads into that unused compute at those times? These are for cost efficiency reasons. These are some of the kinds of challenges we can help work on.
Yeah, excellent. So I think a couple of audience questions. I think people are asking, what's the relationship between Anyscale and Fiddler AI? As you may have listened to, Anyscale is this large-scale model training, deployment, and inferencing product, and Fiddler is focusing on observability. So you can think about those two things as complementary in your AI workflow. So hopefully that clarifies some of those things. So when you're thinking about your AI workflow. So that's a relevant question around that, right? So, there's multiple parts of this AI workflow we just talked about. There's data processing, feature engineering, model training, model selection, deployment, inferencing, monitoring. So when you kind of think about this, right, especially in the Gen AI setting, from traditional AI now to Gen AI, how should enterprises streamline this process? Now some of the things may have gone out of the window. How does what does feature engineering mean in the case of Gen AI or LLM applications? What does model training mean? Is it fine tuning? What does model selection mean? And then of course, we are facing some of those challenges in observability of LLMs. How has it affected you? And what are some of the things that enterprises that you think are trying to solve in this operations of Gen AI end to end?
Yeah. There's so many, different challenges that you mentioned, and the challenges that, like I was saying, the challenges really do change over the life cycle of deploying generative AI, or really deploying different AI applications in production. One of the, we see a couple distinct phases around experimentation and just fast iteration, and then another around scaling and managing many different models, and the kinds of the nature of the observability challenge is very different from previously in machine learning or in traditional applications. The challenges around evaluation are far more complex, and one thing we actually often recommend when people are getting started with building generative AI applications is to front load the model evaluation part, to overinvest in building internal evals early on, because that's going to determine the speed of everything else you do, right? If a new model is going to be released, you're going to swap that in, or you're going to fine tune a model, and then you're going to ask yourself, is the new one better or worse? And you automated evals and that you feel confident in, then you're going to be able to answer that question very quickly. And new models are going to be released all the time, so that's a question you're going to have to ask a lot. And also, evals are one of the things that you can't easily outsource, because they require domain expertise, right? It's
Right. Very accustomed to what you have.
And the same is true with the way you sort of craft the the data, your specific data, into a form that can be used by the AI application, right? There are things that are I think easier to factor out or easier to outsource, in fact, a lot of the AI scaling infrastructure components. That's less, or just the performance stuff, making it as fast as possible on the GPU. These are things that you could solve in-house, but are more consistent from company to company. But a lot of the other evaluation and data processing are quite leverage a lot of domain expertise.
Got it. And so when you sort of as your customers think about using Ray for both traditional ML training, deep learning model training, and now expanding to LLM operations, like LLM fine tuning.
Mm-hmm.
How are you supporting that today? For example, would they be able to would they be able to coexist on the same platform that you're providing? And so now customers are also kind of confused, right? There's a lot of options today, for machine learning, this one, for LLMs, that one. How are you sort of solving those challenges for your customers? Because there's clearly these two worlds have emerged in the last couple of years.
Well, I think people that we work with don't tend to want a different tech stack for LLMs and another tech stack for computer vision models and another one for XGBoost models. If you can have a common platform or framework that supports all of these things, that's advantageous. Especially because AI is evolving very rapidly, moving very rapidly, right? There are going to be new types of models released, new optimizations, new frameworks. And so if you are a lot of companies have gone through this big migration to enable deep learning from classical machine learning, and only to find at the end of it that they need to change things again in order to enable LLMs. right? And that's not the end of it, right? All of these models are going to be multimodal, and
And the agentic workflows are coming in.
they're going to become more complex, right? So from the perspective of like the ML platform team, right? The people who are providing AI capabilities to the rest of the company, you really want to optimize for flexibility and being able to being relatively agnostic to different types of models, different types of even like hardware accelerators, different types of frameworks, right? When it comes to, I wouldn't just like just only support XGBoost or only support PyTorch, right? Or only support one inference engine, right? The more that you can position yourself to be able to immediately take the latest thing off the shelf and work with that, the faster you're going to be able to move, because those new things are going to come.
Right. So let's say like, in the GenAI case, right? So if I were to fine tune, say Llama for my business use case, could I basically have like a Ray inferencing module that would load up my fine tuned Llama and help me scale my inferencing? Like how would, like, if I'm like an engineer doing that, like what would that process be?
Yeah. So Ray has, there are really two layers to Ray. Yeah. There's the core system, which is just scalable Python, basically. The ability to take Python functions and Python classes and kind of execute them in the distributed setting, right? Yeah. And then, that's where the flexibility of Ray comes from, because with Python, functions and classes, you can kind of build anything. But it's too low level, right? If you want to do training, or if you want to do data processing or fine tuning, then using that API, you'd have to build all of the training logic and data processing logic on top of these just functions and classes, which is too low level. And this is why Python has a rich library ecosystem on top, and pandas and NumPy and all these different tools that you can just use off the shelf to build powerful Python applications. And in the distributed setting, Ray tries to do something analogous. There's the core API, which is like Python, and then or scalable Python, and then there's an ecosystem of scalable libraries, and certainly not as many as Python, but these include libraries for training and fine tuning, libraries for data ingest and pre-processing, libraries for serving, right? And that is and they form an ecosystem, which is really powerful, because in order to do training or fine tuning, you also typically want to process some data and load some data. And so the fact that you can do these together in a single Python application is pretty powerful. Instead of, I had run my big Spark job to prepare the data, then I pull up a new system like for training, and I have to like glue these things together and manage a bunch of different frameworks, right? The way people were doing things before is often more analogous to taking each like Python library and making it a standalone separate distributed system, when what you really want is a common framework with different libraries on top that can all be used together.
Yeah. So now when I'm actually doing that productionization, right? So how do teams, like how are you seeing teams kind of maintain that consistent high performance and accuracy across these multiple production applications? What is it that you found out? Are they evaluating the same metrics, before, pre-deployment and post-deployment of GenAI applications? What are some of the other considerations around scalability, throughput that they are looking at?
Yeah. So you're talking about like quality metrics?
Quality, cost, performance. Give us like a catalog of things that your customers are looking at, pre and post deployment of GenAI.
Certainly, some of those ones you mentioned, quality is probably the hardest to measure, but also, probably the one that's foremost, the most important. And then latency and cost are really big ones. And even, it might sound straightforward to measure latency, but there are a lot of subtlety measuring latency, especially for LLMs, where you have, you don't just produce one output, you produce a sequence of outputs. And depending on the application you're working with, you may care about the time to generate the first token, or you may care about, how many tokens per second you're generating. And you may care, this may vary from both of those numbers can vary quite a bit depending on the amount of load on the system, right? The degree to which you do batching. And so we often expose knobs for sort of making that trade-off of sort of more model replicas or lower batch sizes to decrease latency for generating new tokens, or but at the cost of throughput. And there are some trade-offs like that, and there are a lot of optimizations you can do to improve both of these things.
And what have you seen customers do in such a scenario? Like, are they writing custom evaluators for these things? And what have you seen customers do when they're trying to evaluate the quality of models?
Yeah, I mean, the starting point is always to, and on the quality side, like of just how well the thing works, starting point is always to look at the data by hand and kind of score quality and come up with good like reference examples and that you can kind of run benchmarks on. And it can be done with a small amount of data, but you're often hand labeling a number of examples to begin with. And we also see people using AI quite a bit to come up with these reference examples, like come up with hand labeled examples. Like, for example, one of the applications we built in-house was just question answering for our documentation, right? If people want to use Ray, here's a chatbot you can use to ask your Ray questions and get answered, right? And so we wanted to come up with evals for this so that if you, if we swap in a new model, right, Llama 3.1 or whatever, then we can evaluate quickly how good that was, whether the change was beneficial or not. And in order to generate the evals, what we did was sort of to generate a synthetic data set of questions and answers. And we did that by taking our documentation, so randomly selecting like one page from the documentation, feeding it into GPT-4 and asking GPT-4 to generate a some example, some questions and answers, or take a passage and generate a question that can be answered with that passage, and then pairing those together to form your data set, and then using those to evaluate your again, when you run the evals, you have the system take in a question, generate the answer, and then compare that to the reference answer, and you have another LLM do that comparison. And so there are a lot of steps and a lot of like AI being used, but those are like that's a common pattern.
Yeah. So I mean, this is kind of interesting, right? Early on, like in ML world, evaluation used to be evaluating a closed form function, root mean square error or like precision recall. But now evaluation means you're running a model for another model, right, as you just described. And are you seeing like this growth of evaluation models like in customers? Like are you seeing that take off?
Right. It's so funny. It's in the past, model evaluation was, what do you mean model evaluation, right? It's just, you just compute the accuracy and how many of them does it get it right and how many does it get wrong. But that's is very different when the output is a sentence or an image.
That's right.
By the way, the whole field has really shifted in a lot of ways over the past decade, right? I'm sure you remember, as after in the years after ImageNet and after everyone was excited about deep learning, there's a lot of the field was driven by the ImageNet benchmark, and every year people coming up with new models that performed better on the ImageNet benchmark, and the data set was static, right? It was just the ImageNet data set. You split it into your train and test data, and it was all about, can you come up with better model architectures and better optimization algorithms to do better on that data set. And now, the optimization algorithm is more static, right? It's like variant stochastic gradient descent. The model architecture is, of course, there's still a lot of innovation there, but it's more static than before, the transformers and so forth. And all of the innovation is really going on the data set side, right? That was like considered a static thing in the past, and now that's actually where people are putting all of their energy and
Yeah.
tons of money and using lots of AI to curate the data. And that's just a complete paradigm shift.
Yeah, absolutely. Awesome. Let me take some audience question. I think there's some questions around training aspects of it. There's a specific question of how do you differentiate between PyTorch, DDP, and Ray distributed training library? Are they complementary?
They are complementary, and so you can use Ray. Most people using Ray use Ray along with PyTorch or with different deep learning frameworks. And one way to use Ray is to take your PyTorch model, and we have a Ray train wrapper, which you can pass in your model, and then we can set up. Ray will set up different processes on different machines and set up DDP or other distributed training protocols between the different PyTorch functions in the different processes. And so essentially, in that case, it's like a thin wrapper around DDP, around PyTorch. And what Ray is adding is both like setting it up easily, having a standardized way to do this across different frameworks, and the also a way to handle the data ingest and pre-processing and to feed that in, as well as the fault tolerance pieces around handling application or machine failures. So it is very complementary. You can, in some sense, you could think of frameworks like PyTorch and other, and also various inference engines like VLLM, TensorRT LLM, as being focused on, running the model as efficiently as possible on the GPU or on the set of GPUs, and like really single machine performant. And then Ray handles the multi-machine scaling challenge, like a lot of the distributed systems challenges. And so those, are very complementary things.
Yeah. So, how does, I guess the question is probably around like RAG and embedding, maybe like how does it work, about those use cases? Maybe you could take some specific examples of, customers developing RAG applications or on top of like your platform.
Yeah, so there are many different pieces to the whole RAG pipeline, right? There's, of course, there can be, and you may do a subset of these and not all of them, but there's first of all, there's embedding computation, right? Which involves taking your data, processing the data, and there are many decisions to make about how you process and chunk the data and compute the embeddings. Like that can also be a large scale problem or a small scale problem, depending on the data you have. But the data pre-processing and like letting you iterate there, and scale that's something that Ray does very well. Then there's also the actual real-time like inference part, where you are serving requests, right? And there's often a number of models being composed together to do this. It's not necessarily just one LLM, right? You have the retrieval stage, where you are retrieving different pieces of content based on your embedding of the query. You may use additional models to sort of rank the context and decide what context to feed into the model. Right? You also can use other models to rewrite the query and before you embed it. And then once you are, then you feed that into your generation model, you can generate the output. You may have other models kind of fact check or check the correctness of the model. And so the way you're doing serving is actually often running many different models together. And that's something we didn't talk about as much, but the inference problems we see with Ray are often starting to have more and more models deployed together, not just a single model, and many calls to different models. So there's the serving side of things, which can have a growing amount of complexity. And there's also, this iteration loop where you need to continually improve the quality of the application, right? It's not just the quality of the model, right? It's the quality of the end-to-end application. That may mean fine-tuning the model, right? It may mean, but it also may mean fine-tuning your embeddings. It may mean chunking your data, your original data set in different ways. And so it's actually very important to kind of develop unit tests for different stages of the RAG pipeline, right? Because if you swap you make some change, and it gets better or worse, say it gets worse, you need to know what got worse, right? Is it the generation that got worse? Is it that you fed the wrong context in? Maybe you ranked the context incorrectly. Maybe you retrieved the wrong context in the first place. So there's a whole, software engineering practice that needs to be built up around this in order to really like unit test these different pieces and sort of quickly identify where the room for improvement is. And where Ray comes in, or Ray doesn't solve all of these pieces, but Ray is useful for all of the compute pieces, the data handling, the fine tuning, the serving, and so that the people developing these RAG applications can focus mostly on the application logic and how information is flowing from one place to another.
Got it. That makes sense. And so I guess like people want to know how it differentiates from using like this whole RAG architecture that is emerged, like using a vector database and a modeling layer and an orchestration system together to sort of like hook up your RAG application. Let's say you use one of the open source vector databases, say Quadrant or whatever, and maybe you have a Llama and you're trying to put all of these things together through a Llama index. How does that workflow differentiate from like using something like any Ray and what are the pros and cons?
I mean, they're complementary. In fact, Ray doesn't. Ray's very focused on the compute pieces.
Okay,
don't actually provide a vector database. We don't store your embeddings. That is, and so people who are using Ray to build RAG applications are using Ray along with a vector database or along with Llama Index and these other tools. So where Ray ends up being really useful is when, again, if you're running everything on your laptop, then that's fine. And that's not the regime where you need Ray. Of course, it can be useful on your laptop for using multiple cores and stuff, but where Ray really adds value is when you need to scale things and when it starts to, some step of the process starts to be too slow. Maybe you need to fine tune on, more GPUs, or maybe you need to do the data preprocessing on more CPUs and just, and these kinds of things.
Yeah, basically moving from single node or like workstation-based RAG applications to like a distributed, highly scalable RAG application using that compute layer. Essentially,
and giving you the experience, but making it feel very similar to just writing Python on your laptop.
Yeah.
By the way, I actually want to just emphasize the sort of complexity we're seeing around inference, because that it's been growing quite a bit. And you think of machine learning serving as taking a model and hosting the model behind an endpoint and maybe, auto scaling the replicas of the model.
Right.
But we're starting to see applications or, AI products that people are building where they want the AI, they want their product to sort of complete an end-to-end task, like booking an Airbnb or sending an email for you, or making a reservation at a restaurant, or these kinds of things. Writing code is another example.
Yeah.
And that is not the way they're at least architecting these today. It's not a single call to a single model. And if you want to write code or you want to book an Airbnb, there are many steps, right? You have to take some vague description that a person said about what kind of vacation they're looking to have, turn that into different. You may have a model turn that into sort of different types of requirements. You may have another model retrieve different like candidate Airbnbs. You may like have another model score each candidate against the different criteria. You may have a model like generate an explanation for each of the top ranked Airbnbs, like why that is a good choice based on the criteria. Like I'm sort of oversimplifying it, but completing these end-to-end tasks often involves many calls to different models. And so you end up with a serving challenge that's not just a single model behind an endpoint. It's like highly dynamic, where you have calls to different models that are determined based on the output of previous models. You may start with GPT-4 for all of these just to prototype and get it working. But when you have hundreds of model calls stacked together, you often at some point find that hey, latency really adds up, the cost really adds up, and you don't actually need a fully general purpose model for each of these things. You kind of in some cases a smaller specialized model that's really good at one thing may do the trick, and so you end up starting to use fine tuning and of open source models and composing these things together. So it can actually get quite tricky, and I think this is the direction that inference for machine learning is going in. That in the coming years you're going to see very complex serving systems that have huge amounts of models being composed together in a very dynamic way to complete complex tasks.
Absolutely. I think there is this whole notion of model merging that has emerged, where people want to blend these different models and merge together response and hook up these workflows. This is great. So I guess finally, as you sort of describe the sort of the stack, you may have a vector database, you can have a modeling layer of your choice, you can have an orchestration system, you can have I think an array, and can function as this really robust distributed computing framework to bring all these together. And then how does observability fit into this thing? For example, would you consider that as an additional add-on into this workflow to evaluate these metrics that we talked about?
Yeah, I mean, I think of observability as critical, and it comes up in a lot of ways because, you often think about how hard it is to develop an application, but where a lot of the time is spent is really debugging when something goes wrong. And many things can go wrong. It can be that something is not behaving correctly, or it could be something is crashing, or it could be that it's working just fine, but it's too slow. Right? There are many forms of you could be debugging performance issues or debugging correctness issues. And that is something that we've seen people spend countless hours trying to resolve. And if you don't have the information readily at your fingertips that you need to answer those questions, then you may have a really bad time. And so it's often, of course, sometimes you don't know what information you wanted to log or store until the error happens, and at that point it's too late. And so it's very hard to run production systems without observability tooling. In fact, it's really essential.
Absolutely. I think that's a great sort of line to sign off at this point. So, thank you so much, Robert, for joining us on this webinar and sharing your valuable thoughts. I've learned a lot on this, and I think for those of you who are thinking about moving from workstation-based AI development for prototyping to productionization, please definitely look at Ray and Anyscale. They're doing some great work working with tech-forward companies. And then, of course, we, as you sort of think about observability, we are always there from Fiddler to help you out. That's about it from this week's AI Explained. We will see you later with another amazing guest in the future. Thank you so much, Robert.
Thank you.